Our physical model in its most isolated state, a single point charge radiating force into a dark void. This microscopic particle contains energy, but shifting from a mathematical abstraction to a functional macroscopic electrical system requires a different way of modeling physical reality. Our destination is the parallel plate capacitor. Engineering the storage of electrical energy relies on manipulating physical geometry to trap electric fields. By shifting our mathematics away from tracking particle-to-particle interactions and toward the geometry of empty space, we gain the capability to engineer the electrical grid. The system rests on the fact that electric charge is a conserved intrinsic property of matter. It cannot be created or destroyed. This illustrates Coulomb's law, where the electrostatic force between two charges drops off exponentially as the distance between them increases. Coulomb's law requires us to visualize an instantaneous physical pull operating across a void between distinct particles. We transition to the electric field model. Instead of one particle reaching out to pull another, a single charge modifies the properties of the space around itself. The electric field is the foundational architecture of electromagnetism. Everything built in electrical engineering relies on shaping this field. This reveals the problem with applying Coulomb's law to a macroscopic object. A simple piece of copper contains trillions of interacting charges, creating a mathematical gridlock of overlapping forces. At this scale, tracking every individual vector becomes a practical impossibility. We resolve this by measuring electric flux, the total amount of the electric field piercing through a specific designated boundary. Gauss's theorem proves that the total electric flux radiating through a closed mathematical surface is strictly proportional to the net charge enclosed within it. The internal distribution of the charges is irrelevant. Only the total net charge dictates the flux passing through our boundary. By linking fundamental charge directly to the geometry of macroscopic space, Gauss's theorem allows us to bypass trillions of individual macroscopic interactions. Mapping the electric field as an energy landscape allows us to visualize peaks of high potential energy and valleys of low potential. Electric potential is the exact amount of work required to push a test charge against the electric field lines, forcing it up one of these topographic peaks. To control this potential, we use conductors, materials where internal charge can move with zero electrical resistance. Because like charges repel one another, any excess charge injected into a conductor migrates to the extreme outer surface to maximize the distance from its neighbors. This surface migration ensures that the internal electric field of any solid conductor is exactly zero. Since the internal field is zero, the entire conductor operates as a single equipotential volume, providing the rigid boundaries needed to shape external electric fields. The parallel plate capacitor is constructed by placing two conducting boundaries opposite one another to generate a controlled potential difference. When energized, positive and negative charges distribute uniformly across the opposing inner faces of these metal plates. This geometric arrangement forces the electric field into perfectly straight, uniform lines between the boundaries, trapping the energy inside. Capacitance is the ratio of stored charge to potential difference. It is a function of physical geometry, dictated by the surface area of the plates and the distance between them. We optimize this storage by inserting a dielectric, an insulating material, into the gap. Inside the dielectric, atoms operate as electric dipoles. Under the stress of the capacitor's field, these dipoles rotate and align themselves against it. This alignment generates a secondary, opposing field that partially cancels out the primary internal field. Weakening the internal field lowers the potential difference. Mathematically, this allows the plates to accept more charge for the same amount of effort, increasing the dielectric constant. Dielectrics allow engineers to bypass the geometric limits of empty space, multiplying the energy capacity of the hardware. This high-level view of a capacitor circuit represents the macroscopic application of classical electrostatics. The energy exists invisibly within the geometric tension of the constrained electric field. From this single unit, we build complex grids by wiring capacitors in series and parallel. As the physical layout shifts, total capacitance scales mathematically, allowing precise control over energy storage. This progression moves from forces of isolated charges to continuous vector fields, utilizing Gauss's geometry to maximize the system. Massive energy storage systems sustaining the modern grid operate as highly scaled projections of spatial geometry.